All right, so today we're going to cover something called the divergence theorem. And we remember the divergence of a vector gives us a scalar valued function. It does not give us another vector. So just to remind us, if I said the divergence of some vector f, where let's say f is equal to m and p, sort of the usual m, n, and p, all functions of three variables, then the divergence of f was simply the partial of m with respect to x plus the partial of n with respect to y plus the partial of p with respect to z. But we could also think about it as a dot product of these two things, which is kind of an odd way of looking at things. But the reason I like to think of it as the dot product is the dot product means I will not get a vector in the end. I will get a scalar valued function. Remember where this is the operator, and I'm applying the operator to each term, and then I'm adding the results as in any other dot product. So this is kind of a formal way that people learn it, but actually that's all you're really doing. You're not really going to set it up this way. You're just going to do this. And in almost every problem you'll run across, this quantity here is a heck of a lot simpler than maybe what you started with, because again, it's partial derivatives. There's usually less stuff. You might get a lot of zeros in there. So that's what the divergence of a vector is. We've had no use of this yet. It's just there. We introduced divergence and curl at the very beginning. There are a lot of calculus books that will actually introduce divergence and curl at the end of this chapter because you haven't used it yet. We used curl for the first time last day to actually produce an answer, right? But we're using divergence today. But the reason I like introducing curl early, it's the only way I can check to see if a three-dimensional vector is conservative. Oh, okay, because we proved the curl of that vector would have to be the zero vector if it's conservative. So that's a good reason to have curl early. And it doesn't make sense to introduce curl early and then not introduce divergence, because divergence is actually way simpler. So let's start. Here's the situation. Multiple pens here. Last day we learned how to deal with a surface. So I want to kind of set us up. So here's what we did last day. I have a surface, and I want to find the flux of this surface. A surface, think of a surface literally like a sheet floating in the air. There's no volume. Don't even think of it as having thickness. I mean, it can be infinitely thin. I have a sheet. I'm putting that sheet in the river and water is flowing through it, and I'm measuring the flow of the water, right, per unit area. But that's mentally it's a fairly simple picture. The calculation we saw was kind of gnarly, right? It was F dot NDS, and we did some work. What if instead of being a thin sheet, I make this into a three-dimensional solid? Ooh. I make this into a three-dimensional solid, and I say, now, I want to find the flux for this thing. How would I do that? Well, I'd have to do each surface. Now, the absolute simplest three-dimensional thing you could have, believe it or not, is a sphere. Why is that the simplest three-dimensional thing you could have? Think about it logically.
It's symmetrical on all sides.
Yeah, I mean, I could make it an oval, but the idea that if I cut the sphere in half, I can describe the sphere with two separate surfaces. My picture here, I have probably 6 at least. Does that make sense? Oh, so the sphere we like because there's a top and a bottom, there's not sides. Now, here's what I want you to think about. At my house, we have a round table that we used to use for meals, and it's one of these old-fashioned tables where you can pull it apart and put in leaves. Everybody seen one of these before? And we would put in the leaves to extend the table and make it wider. So this is exactly what I'm doing. I want you to think of something. I have a mass. I have a blob on my desk. And it's a simple three-dimensional blob that if I cut my blob in half, I'd have a top half of the blob and a bottom half of the blob, so I only have two surfaces. So what I'm going to do is cut my blob in half and insert leaves. I'm going to extend my blob. Why? I'm going to add a whole bunch of lateral sides to my blob. I'm intentionally making my blob more complicated. Is everybody okay with that? So I now have this blob with leaves. So this is my Thanksgiving meal blob that we're all going to sit around. So I have a top, a bottom, and I actually have lateral sides. So that's what I have here. I have lateral sides. Now the lateral sides have to be vertical. Why? Because if the lateral sides were angled, then they'd still be part of the top. Is everybody okay with that? Oh, so if I have a sphere, I cut the sphere in half and I extend the sphere vertically, then the vertical is not part of the top. But if I cut the sphere in half and extend the sphere this way, this is still part of the top. It's still part of the same function. It's when I get vertical that it's no longer part of the function. Does that make sense? So that's what I just did here. So this has a top, it has a bottom, and it has lateral sides that are horizontal compared to the top and bottom. I've intentionally made it complicated. So when I asked for this, over the surface, I now have a whole bunch of surfaces. So I want you to think of it this way. All right? I'm going to call this surface 1. I'm going to call all of the lateral part just generically surface 2. You'll see why I can do that. And then I'm going to call the bottom surface 3. It's pretty complicated. Can you see over there, Donnie? Okay. I know that. I won't go any lower than this because I know there's a computer in the way. All right? Now, let's call this z equals u of xy. And then we'll call this guy z equals v of xy. Right? They're completely unrelated. So the top surface is still a function of two variables. The bottom surface is still a function of two variables. So with that, I have a normal here that's going to point upwards. And we'll call this guy normal 1 because it goes with surface 1. I'll have a normal here that's going to point downwards. By the way, I'm just generically pointing it upwards. It's pointing above the xy plane. It's not necessarily parallel to the z-axis. Right? But we all agree it's going up because this guy's going down. And now here's the key. Tell me about normal 2. Normal 2 must be going parallel to the xy plane because I inserted vertical leaves. If my leaves aren't vertical, then they are still part of either the top or the bottom surface.
Is it just do normal 3 or normal 2?
Oh, I'm sorry. Sorry, thank you. Sorry. I want those to match. Thank you, Bodhi. Yeah, that would be a problem later on. Everybody cool with that? So, nothing complicated yet, but this sideways thing is actually really, really important to my big picture. So now, I'm going to do something here. I'm going to break up the problem, okay? So I'm going to do the following. My force vector, which of course is M and P, I'm going to break this up as follows. I'm going to walk you through the whole thing. By the way, the notes are posted online. So if you get a little bit lost or it starts feeling like the Matrix movie with all the symbolic notation, feel free to just watch. Anyway, so I've got this. I want to change this then to can I do this? Is this legal? Yeah, I want to do this because I'm going to break all of this problem up into small bite-sized pieces, okay? So that means at this point, this thing here is now, let me make sure I got all the right notation here. Yeah, bound with NDS. Okay, so there's no ambiguity there. We all agree that that's a true thing. Now, I need to get and break this up further. When we had multiple curves on a line integral, we just called it generically C. But then later we said C was actually C1 union C2 union C3 and so on. Do you remember doing that? Okay, because it's generically, this is over the whole surface. But technically I have multiple surfaces here, don't I? Oh, so that means I'm going to rewrite this. You'll see why we're breaking all this up. This technically is what? S1 plus S2 plus S3. I have the flux through the top surface, the flux through the lateral surfaces, and the flux through the bottom surface. Because technically, and this is the most important part, S is this. And like we did with the line integrals, if my curve is the union of other paths, then I would add the integrals to produce the entire path. Okay? All right, so now, yeah, that's exactly what I want. So here's what we're going to do. We're going to take one of these pieces only. When I proved Green's theorem, remember, I took one of the pieces. I took the M, and then we went all the way through, and then later I took the other piece, the N, and then we went all the way through, and then you guys saw the results and go, oh, wow, that's so cool. And if you went backwards, after I did the M and got its result, you might have been able to predict the result for N, because you knew it was going to look really similar. And this is kind of what this is going to be. I'm going to take just this piece and take this all the way through to the bitter end and get an answer for this guy. I'm not going to do it for all three because I'm going to end up using all of these boards twice if I do that. But I'm going to do one of the pieces all the way to the bitter end, get the conclusion for the one piece, and then you'll see, oh, I can easily fill in the blanks what the other two pieces would be. You guys okay with that? For me to do each piece would take a ridiculously long time, and I'd be repeating a lot of the algebra. So what we're going to do is concentrate on this piece and this piece only, and we're going to calculate what this is. Then when I do that, you'll be able to tell me what this is, and then you'll be able to tell me what this is to its completion, because the algebra is going to be really similar. Okay? So now that I have all of this gobbledygook, I need to get rid of some of it. Let's see, let me use blue so I can separate these guys. All right, so I now want to take this piece here. And I want to rewrite it as now there's something that should just jump off at you almost immediately. I've generically put an n in each position. Is that the same n in each position? No. On surface 1, very specifically, what n am I using? N1. Oh, does this matter? Yeah, this matters hugely. Then what am I doing here? N2. What am I doing here? N3. That's why if I break it up into the individual surfaces, then I use the individual n's. Now, 1 and 3 are going to be a bit of work, because obviously I'm going to have gradient vectors that I'm going to have to produce. I'm going to do a lot of work. Tell me about that middle one, though.
Zero.
Why?
Because the force is perpendicular to...
This is only pointing in the z direction. This is 0 in the z direction. In other words, what is n2? It's in the form something, something, 0, isn't it? Because it's pointing horizontally. Does everybody see that? These are orthogonal. This is pointing horizontally, this is pointing vertically, so right off the bat, we can do this. Ooh. Now, by the way, if I had done this one or I had done this one, in each case, one of them will have something that would cross out for being orthogonal. You said, like, what do you mean by something orthogonal? Well, if I looked at something that was only pointing in the y direction, wouldn't it be orthogonal to the z? If I had something pointing in the x direction, it would also be orthogonal to the z. I have something pointing parallel to the xy plane. Okay, so I've got this now. Oh, sorry, this is S3. Sorry. So now let's break this down. So now what I need to do is figure out the individual normal vectors. What are they exactly? All right, so I need to do gradients for both of those. So we're going to invent new functions. Let's call them g, because I haven't used g yet. So let's do the top one first. Let's call g1 of x, y, z. What do you want to call it? Remember, you have two choices. Is it z minus u or is it u minus z? And there's no ambiguity. This is absolute.
Z minus u.
Why has it got to be z minus u?
Because it's pointing up.
Yeah, I need the partial with respect to z to be positive 1 versus negative 1. So everybody already knows what the bottom one's going to be, isn't it? It's going to be v minus z So the partial points downwards. That's why I made a big deal of this earlier on. I said, you have to know what the thing looks like because it can't be ambiguous which way your normal's pointing. If I have the normal pointing the wrong way, everything about the thing I'm deriving won't work. Oh, so I need this to be z minus u of xy. Cool. Okay, so then what's the gradient of g1? It would be negative ux, negative uy, positive 1. Okay? Similarly, let's do the same thing for the lower one. Let's let g2 of xyz. Now, well, I'm sorry, let's call it g3. Sorry, let's keep them matching. Which way do I want to go here, do we say?
U for V minus Z.
V minus z, so v of x comma y minus z. Nothing I've done is complicated so far. Nothing I've done conceptually should be giving you issues. We're going to do some calculus in a moment, but we really haven't done anything yet. We're just still in the setting up stage. So then my gradient will be vx, vy, negative 1. Because I need my gradient vector to point downwards, because now I'm going to make my normal vectors.
It's G3.
Oh, I don't know why I want to keep changing the numbers. Thank you. Okay, everybody cool with that so far? Okay, no big deal. So now I want to define my n1 and my n3. So then what is n1? It's 1 over the gradient of g1 times this. And what is n3? I got that number right. It's 1 over the gradient, or I'm sorry, the magnitude of the gradient, not the gradient, sorry. And vx, vy, negative 1. Now this is important because we're going to actually do the dot products in a little while. And we're going to do all the flux stuff that we learned last day. We're going to do all of that to this stuff in just a moment. Okay? Now, one of the things we now also know, going back to here, this is my f of xy. So when I'm doing the surface area parameter, which is unrelated to the normal vector, we had to come up with a normal vector. The surface area parameter only is taking this into account. Right? And taking this into account, remember fx squared plus fy squared plus 1 under the square root? Aha. So let me put it over here. What is ds1? Fx squared plus fy squared, well in this case, it's not f, it's u. Okay, so ux squared plus uy squared plus 1 dA. And what's ds3? Well, that would be vx squared plus vy squared plus 1 dA. We know this. This is not new. This is surface area stuff. So when we do the flux and we set everything up, that quantity right there is going to cancel with that quantity right there, isn't it? Because that's exactly what the magnitude of the gradient vector should be. It should be this if I did it right. Well, then why do we go through all this? Why don't we just jump forward? Because I will get the signs incorrect if I just did that. I got to get the signs correct. That it does matter that I clearly state what the normal vector is, including what direction it's pointing. Then when I do the algebra, things cancel beautifully because I set it up correctly. So now I'm going to erase some of this so I can fit this in. So what do I have now? I want to write this over the region in the xy plane now. So when I do this dot product, that's p of xy. I'm sorry, that's p of xyz, correct? When I do that dot product, I'm dotting it with this, remember. So I have 0, 0, p dotted with all of this. This is kind of nice, isn't it? Why? 0, 0, p. Oh, that's kind of hard to get wrong, isn't it? So what's the first one going to be? It's going to be just p, then what? Oh, that should be, you know what? Oh no, I'm going to leave it as ds. That's still the generic ds. But isn't that going to be dA? dA? Yeah. Agreed? Oh, that's not so bad. We're going to have to fix something in them. You know what I just, let's see. I just realized something. I've been writing these as single integrals all this time. My bad. I'm looking at this going, wait a minute, these should all be double integrals. I'm sorry about that. I have to go back and edit the videos. These are all double integrals, not single, because we're doing flux. Okay. So this is still a double integral. But like we saw last day, I have a double integral over 3 variables. We'll fix that in a moment. Plus, now let's do this guy. What's that going to be? 0, 0p dotted with this guy. That's also pretty simple, isn't it? And what is that going to be? Negative p of x, y, z dA. Now, this part is the same in both. This part is not. These are not the same z's, are they? The first one is using this z, the second one is using this z, and because it's a double integral, I can't have a third variable, so now I'm going to swap out the z. This should feel very much like the Green's theorem proof. Remember, we had y's, I swapped it out for f of x's and g of x's. So what am I going to replace this with? It's important that we see that. I'm going to put the minus in front then, just make this prettier. And this will be p of x comma y comma v of xy. Yeah. All right. I am feeling much better now about this. I have 2 double integrals, by the way, that may not be terrible. These might actually be fairly simple to evaluate, but I'd still have to go through and do everything, right? There's still a lot more to do. Okay, make sure I'm in a good place here. Now, because the region in the xy plane is the same and the dA has to be the same, can I just make this one integral? Seems reasonable. I think I can erase this stuff now. Hate doing this, but this is all being recorded anyway. So this, let's just write it this way. Region in the xy plane of p of xy u of xy minus p of xy v of xy dA. All right, I'm happy with that. You know, looking at the integrand, doesn't that kind of look like something that was a triple integral that was evaluated? Like at these 2 limits of integration? That's where it should feel very Green's theorem-ish right now. Does everyone see it? This is exactly the same kind of situation we had with Green's theorem. What did I have to do to get to here? So now we're going to work backwards from a calculus standpoint. If I said, here's a triple integral, integrate it, you're going to eventually get a double integral, eventually a single integral. What had to take place in the step before? Well, wouldn't it have had to be something like this, p of x, y, z, evaluated what? U of x, y at the top, v of x, y at the bottom. Does that make sense?
Doesn't it have to be a triple integral?
Not yet. I've evaluated the triple integral, and now I would have this. Does everybody see this? So if I said evaluate this, you'd have this. So now what triple integral produced this? Again, this should feel very Green's theorem-ish. Bring this up high so you can all see it. What did it have to be? Well, first of all, what integration did I have to do? I had to integrate with respect to z, didn't I? So I have to have something, and I'm going to just generically say dz, dA. dA is obviously either dy dx or dx dy. That doesn't matter, you choose it. But the dA is clearly from the region of the xy plane. This is not really clean yet. But it's very clear that what I want is this. What did I have to integrate? And obviously these limits, by the way, this would be v of xy, this would be u of xy, and the rest of this would still be the region in the xy plane. We'll eventually describe it as a 3-dimensional thing. What has to be there? What do I have to integrate with respect to z to get p?
P of x, y, dz, d, no, that doesn't make sense.
And what do you have, we did this before. What do I have to integrate to get something? I have to integrate the derivative. Don't have to integrate the derivative, but what derivative very specifically?
Oh,
The partial of p with respect to
z.
z. Ooh. Again, this should feel familiar. If I integrate the partial of p with respect to z, and I integrate with respect to z, I should get p. I was like, oh, okay. So let's leave that alone for just a second, because now am I integrating over the entire volume? Now? dz, dr, yes. So I'm going to rewrite this like this. Now, in the textbooks, we don't really have a symbol for integrating over the volume because we went from surface to region in the xy plane. We're very specific. So a lot of textbooks will just put a V here, integrate over the entire three-dimensional shape. Some textbooks use the letter Q. I think in my notes I used the letter Q. It doesn't matter what symbol you use. You're just saying over the entire shape. If I had asked you to do something using spherical or cylindrical coordinates to find a volume, you would understand. I'm going to set up 3 sets of limits of integration. If we were doing something like the tetrahedron, bounded by planes, that's fairly easy. But you'd set up your limits because you're integrating over the whole volume. I'm just saying you're integrating over the whole volume. The limits are whatever they are, But this is what we get. So I'm going to stop right now. What does this equal? Where did this come from? At the very beginning of this problem. This was the double integral over the surface of 0, 0, p dot n ds. This was the flux applied only to the p. Because way back here when I broke this up into 3 pieces, and this was over the entire three-dimensional surface. This was not over S1, S2, or S3. We broke F up into this form at the very beginning of the problem. And I said, let's only look at this piece here, and this is the answer we get. If I do the exact same process, let's say I do it for the m, we get an answer. If I do it for the n, and here's the part that hopefully you'll see then. Let me write up top. This is the part I'm going to skip because it would take all of the work I just did. I'm going to do 3 times. But I'd have to keep redefining things. In other words, right now we have a top and bottom surface. Then I now have to describe lateral surfaces. And it gets messy. This is over the entire surface, over all of the different ends and everything. What do you suppose this ends up equaling?
dm dz. Oh.
Partial
dm
with
dx.
respect to x.
Exactly. Integrated over the volume. That's exactly what you would get if we did the entire process to that guy. Oh, and while we're at it, what do you suppose? And just be thankful that I'm not doing all of them. It would take forever. What do you think this one ends up being?
Partial of n with respect to y.
Partial of n with respect to y. Integrated over the volume. So now let's go back to the very beginning. I have a 3-dimensional globular surface. Yeah, we actually inserted leaves into literally to make it more complicated. So most of the time, like a sphere, you have a top and a bottom. I made it more complicated. I give you a top and a bottom and lateral sides just to get this result. You're never going to do this. You're not going to take something and change it. So if I said, hey, here's our thing. It's a sphere. It's a closed off circular paraboloid. It's a circular cylinder. It's just a 3-dimensional shape. It's a cube. I don't need to insert leaves, but I have to start with a 3-dimensional object. You go, okay, now I know what to do. So now the answer to this question, which is broken up into here, this is equal to the triple integral over the volume of the partial of m with respect to x plus the partial of n with respect to y plus the partial of p with respect to z, all integrated over the volume. By the way, what's that quantity in the middle?
Divergence.
That's the divergence of f, isn't it? That's why this is called the divergence theorem. that if I want to calculate the flux of a closed object, okay, I would have to calculate the flux over every surface and add them up, and that's absolutely correct. Man, that could be long, and that could be really complicated. But if I do the divergence of that thing and integrate it over the volume, I will get the same quantity. And we already know that the divergence is probably less stuff, right? Because it's a sum of partial derivatives. It ends up being usually easier stuff. But integrating over the volume means I never had to calculate any gradients, normal vectors. There were no dot product. I didn't have to convert my surface into the area in the xy plane. There's things that I don't have to do. Earlier on with Green's theorem, we said if we had a closed loop, we could just find the line integral over each curve and add them up. And that's absolutely always correct. The day before you learn Green's theorem, that's exactly what you would have done. But when you learn Green's theorem, you say, well, if I integrate over the area, it's probably less work. I mean, I would be hard-pressed to come up with a problem where Green's theorem made it more work. I don't think I could. I think it would always be much less, and a lot of times, way less. I might not even be able to integrate the original stuff. We did examples where we couldn't integrate, but with Green's theorem, we got a really simple thing because of the partial derivatives. So this is just a beautiful theorem that takes this problem here, okay? Now let's do a couple of examples. A lot of people will say this is like a three-dimensional version of Green's theorem. No, technically Stokes's theorem is the three-dimensional version of Green's theorem because you're on a closed loop. But this is a three-dimensional analogy of Green's theorem, not version, because this is not the same thing. Green's theorem was curves that closed. This was a thing, a blob that was closed. You can't equate those, but the way I proved this used all the same types of notions and strategy, let's say. All right, so give me a sec here. Again, these notes are posted on Canvas. They've been up actually for quite a while. So if you want to go look at them, might make it easier. I think in the notes I actually also have the picture. Because when I was doing this way back when on my 3x4 whiteboard at home when I was having to do asynchronous lectures and Zoom lectures, I had to have pictures that the students could look at. And so this one has, beautiful picture, isn't it? Show it to the camera. Beautiful picture. Yeah, I have a lot of pictures. If you looked at one of the previous quizzes where we did the spherical and cylindrical coordinates, you guys remember that picture? I actually did that freehanded. I didn't use a rule. I just did that freehanded on my 3x4 whiteboard. And I had people say, how did you get the lines so straight? I don't know. I got lucky. I can draw circles. I just can't draw lines. That one came out pretty good, actually. Okay, so, hold on. I have an example. There we go. We're going to start simple. We're going to do a couple of examples here. All right, so the question is, we're going to do this. And in Green's theorem, I know to use Green's theorem because symbolically I show that it is a closed loop in the integration. There is no symbol to show that it is a three-dimensional thing. You're just told that when you're told what the surface is. Okay? So in other words, there's no circle or anything like that. Okay? My force is 2x cubed plus e to the yz cos x plus 8yz 2x squared z minus 4z squared. And my surface is the first octant portion of this plane. So it's not just, in this case, it's not just the plane coming through here. It's actually the walls and the floor. So it's the three-dimensional solid that I created by that plane. What is that shape called? You guys remember? Tetrahedron, beautiful. If I was just talking about the plane that cuts through here, we know that's a triangular plane in 3D, and then we'd have the outwards pointing normal, and we do the whole thing to that, right? We do the flux, and we did that last day. But we would have done it on that one surface only. I'm asking you to do it on that surface, on that surface, on that surface, and on that surface. So to do this problem would require 4 separate integrations. Now, some of them would be easy because my normal vectors, right? For the floor, the normal vector is just 0, 0, 1. So in that sense, the setup would not be hard for any of them. I just got to do 4 integrals. I don't want to do 4 integrals. I'm lazy. So I want to use the divergence theorem. So first thing I want to do is, what is the divergence of f? Remember, this is a scalar valued function. This is not a vector. So partial with respect to x,
30x or 6x squared,
6x squared, plus the partial with respect to y of the next term,
8z,
plus the partial with respect to z of the last term.
2x squared minus 4 or 8z.
Do we all agree with that? Yes, no, maybe? Okay, Lena gives me the thumbs up. Oh, these cancel, how nice. So, if I was doing this as a flux problem, I would have to take the gradient to one of my surfaces, right? Do all of that stuff, and when I did my dot product, I'd be dotting it with this stuff, which means, and my integrand would be really big, and I'd be integrating it over a simple region, but I'd have a really large integrand. And now I'm raising things to large powers left and right, and I've got, oh, by the way, exponential functions and trig functions of things that, if you want to on your own set this up as a regular flux problem, you'd say, no, I don't want to do this. I'm going to change my major. This would be really horrible. This is really horrible. But this is really friendly, isn't it? So that's my integrand when I do the triple integral. I'm guaranteed to get the same numerical answer in the end. But if I try to do this as a straight up flux problem, that f dot n ds, I got to use all of this. And all of this is going to show up in some capacity because my normal vector is not going to have any zeros in it. My normal vector is pointing this way out of the plane. Now, my normal vector will be a vector of constants. That's true. Right? 6, 2, 1, and then I make that into a unit vector. But when I said, now let's dot this with 6, 2, 1, all of those terms show up and nothing cancels. I'd be integrating that now over the triangular region in the xy plane. That's what I'm trying to get across. I don't want to do that problem. I really don't want to do that problem. I mean, talk about gnarly calculus. I mean, you'd be doing multiple integration by parts, for one thing. All right. So my problem now is going to be the triple integral of 8x squared dv. I'll put generically over q. Now, I have a tetrahedron. It's probably a good idea at some point if I draw the thing, because I want to get my limits of integration correct. So 2 units in the x, 12 units in the z, 6 units in the y. About right there. So this 3-dimensional solid that I just created. Now, what order do you want to integrate? It does not matter. We know we're going to get the same answer. And by the way, a lot of times we try to avoid fractional things, which is good. Regardless of what order you do, what variable do you want to integrate last? X. Hopefully that is really obvious to you now. If I integrate x first, I'm going to get x cubed, and then I'm going to evaluate my limits, which are linear functions. I'm going to have to cube binomials and... By the way, I get the same answer regardless of the order, but don't do x first, do x last. Again, you don't want to be cubing things. If I do x last, I'll be cubing constants. So that's a way better thing. Okay, Dallas, you had a question?
Oh, I was going to answer.
You were going to give me that. Okay. Again, it does not matter, but you can be lazy and say, you know what, I don't want to make this harder. So I'm either going to go dz dy or dy dz. Now, that does not matter. If I solve for z, I have no fractions. If I solve for y, I'm going to have fractions. I'll go dz first then. How's that? I'm that lazy. And by the way, look at the order we got. That was sort of the natural order most of you would have gone with anyway. Don't make that the default though. Let me throw a what if at you. What if this was 8z squared?
Do z list.
And you gotta do z last. What if it's 8y squared? You do y last. You're doing x last because your integrand only had x's in it. That just makes your calculus easier in the long run. The dz, dy, dz or dz, dy, now you're gonna say, well, I wanna set it up so I don't have any fractional limits. Okay, that just again makes the algebra easier. So z is going from what to what? So if I write the z is 12 minus 6x minus 2y, and I'm going from floor to ceiling. The ceiling is the plane, the floor is the xy plane, so therefore the floor is equal 0. To 12 minus 6x minus 2y. Now I'm in the xy plane. In the xy plane, z is 0. So now I'm 6x plus 2y equals 12. You've already said you wanted to do it this way. So what is this line here?
Y equals 6 minus 3x.
So y will range from
0 to 6 minus 3x.
beautiful. And then finally, x will go from
0 to 2.
yeah, it's in this picture too. See this picture right here? That part right there, we know is that. So x is 0 to 2. I don't think any part of this should give us issues. Yeah, there's going to be a little bit of work. I may have to square something somewhere. That's okay, I can live with that. I just don't want to have to cube, you know, something large. See, if I had solved for x first, then I would have had fractions on the other side, which I can live with, but I would have now had to cube a trinomial, not a binomial, a trinomial in my first step. Yeah, no, I got better things to do. Right. So you got, yeah, I think I would avoid that step. So let's crank this out. So 0 to 2, 0 to 6 minus 3x, and that's going to be 8x squared z. From 0 to 12 minus 6x minus 2y, and then dy dx. So, well, the nice thing is because the other one's 0, I can just multiply these out, and what will I get when I multiply this out? 8x squared times 12, so 96x squared, minus 48x cubed, minus 16x squared y. Do we all agree with that? Okay, and that's dy dx. All right. Now I'm going to integrate that bad boy with respect to y. So 96x squared y minus 48x cubed y minus 8x squared y squared, and y is going from 0 to 6 minus 3x, which is easy here and here, but I got to square it over here. I can live with that. That's probably the worst of the algebra that I face. So, one of the things I prefer to do, the next integral I write, I want it to be clean. I want it to be the next thing I'm going to integrate. Here's what I don't like to do. I'm going to write the integral, and then I'm going to plug in the y's, and I'm going to square it, and then I'm going to square it and evaluate, and then I'm going to gather like terms. I'm going to write integral equals integral equals integral equals integral, and it's still going to be the single integral, which means I'm going to perform all of my algebra within the integral as I write integral equals. That's what most people do. I just find that horrific to read. I don't want to do any algebra within my integral. No, I want to do this. Whoops, not y, sorry. You can always write integral equals integral equals integral, but at some point you got to actually perform the algebra. I got to do this. So here's what I want to do. Equals. Everybody understand? That's what I want to do. I'm not putting an equal sign between here and here. I'm putting an equal sign between here and the finished version. Nobody wants to read, over and over and over and over all the algebra within there, the arithmetic. But I got to take my time because I can't afford a mistake here. So this is 36 minus 36x plus 9 squared. So now when I distribute, I get what? 576x squared minus 288x cubed minus 288x cubed, just a little bit, plus 144x to the fourth, and then over here, minus 288x squared plus 288x cubed minus 72x to the fourth. All right, did I get those correct? I need you guys' eyes and ears here. Are all those correct? No mistakes. We don't like mistakes. We still like the people who make the mistakes. We just don't hang out with them. Okay, I think that looks... Yes, I think that's correct. And in the end, what do I got? I've got, looks like 72x to the fourth. How many? Oh, okay, at least one of those cancels. So minus 288x cubed, and then plus 288x squared. Do I have any other terms, or is that all? I think that's all. Let me see, did that work out okay? Yeah, it's written down somewhere. I believe that's correct. So here I have 72x to the fourth minus 288x cubed plus 288x squared dx. You don't want to go from here to here without showing the work, because if you made a mistake, you're never going to figure out what it was. Do the work. Oh, do the work, but you can always do the algebra on the side. Most of you do that anyway, just because it's really hard to follow. I didn't need to do any work off to the side. All I did was I multiplied these easily enough. This, not so easy. I could try to do that in my head, and I might be successful. 80, maybe 90% of the time. Probably not 100% of the time. So let's finish this up. So what do we got? 72 fifths x to the fifth minus 72x to the fourth plus 96x to the third from 0 to 2. All right, get out your calculators, and let's see what that gives us. Anybody got an answer?
384 over 5.
384 over 5. Beautiful. You know why the answer's a little bit, maybe a little bit of a head scratcher? It's correct. Go back to here. If we had done this as a flux integral, and then I did that in just, the first surface, and I do the dot product with the normal vector, we're going to get all of these functions, aren't we? Including the exponential function. But our answer didn't have any transcendental terms. There was no e's in my answer. You find that a little bit interesting? Oh, by the way, there was also no trig stuff in my answer. So that means the e's and the cosine and stuff really produced 0 towards the answer in the end. Interesting. It's sort of like when you're doing anything with circles and stuff, circles, spheres, and you have a final answer that's an integer or a rational number and it doesn't have a pi. You're always a little bit suspicious, aren't you? Well, there probably should have been a pi there. But maybe the nature of the problem was such that it didn't matter. In this case, we got a rational function, but I didn't have an algebraic Remember, there's only two types of functions that exist, algebraic or transcendental. And this one I always fun with, because I go through this in Calc 1 heavily. The definition of an algebraic function is one that's not transcendental. And the definition of a transcendental function is one that's not algebraic. That's actually the formal definitions. So it's one, you have to know the secret handshake or you can't know the answer to the question. And I have fun with that because people say, wait a minute, it's one if it's not the other, great, but what if I don't know which one it is? Well, that's too bad. Transcendental, trig, inverse trig, exponential, logarithmic. In other words, things that produce essentially always irrational numbers. Algebraic, anything polynomial-ish. Okay, even polynomials raised to powers, because they typically will produce rational numbers based on input. Okay, so in this statement right here, algebraic, 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 transcendental, transcendental, algebraic. That's okay. How many have seen a calculus book where the cover said blah, 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 early transcendentals? About half of all the calculus books. That's the one I prefer to use. That means you learn all your derivatives and integrals. All right. You learn your derivatives of sines and cosines and e's and logs and stuff. Earlier, a lot of folks like using the late transcendentals. The problem with learning late transcendentals is then you get introduced to the inverse trig functions, the derivative of the inverse trig functions, and the integral of the inverse trig functions in the same section. That's the way the Swakowski does it. And the students never learn it. No, you really want to learn your derivatives and then the application of the derivatives completely. And then later learn the antiderivatives of those things. But the ones that have late transcendentals, you learn the logs, what the logs are, you review them, their derivatives and their integrals in the same section. Literally the same lecture. You realize how confusing that is to most people? Okay, all human beings do it that way? No, you never want to do it that way. You want all your derivatives first, learn all your transcendental functions, then later do all your integrals. Because then the integrals are so much easier because you have all the derivative formulas. But if you're learning your derivative and your antiderivative at the same time, then you don't have them, either one of them down very well. But understanding the difference. Now, that problem was not trivial. There was a bit of a work. Let's see. So let's do another one. And by the way, we are finding flux. That is the answer to this question. So in terms of what is it, this would be flow, the volume per unit area of this surface. That's what that would just measure. Okay? Well, so wait a minute, but how do I know what the water, the river that I'm in, how do I know how that's moving? That's what that is. That force is the force of the liquid that's passing through it. That's not something else. You have a solid object, you're placing it in the river, and that defines the river's flow. Is this a constant flow? No. How many have ever done whitewater rafting? Anything like that? When you're whitewater rafting, you can be at a portion where it's just crazy wild, and then you go several feet away, and it's like it's not even moving necessarily. In fact, over here it might be like little circular portions moving around, yet over here it's crazy wild. So that's how you get out of the boat. If you're in the rapids, you go to the area where it's not moving, yet it's all the same river. It seems wild. It seems like it should all be moving at the same rate, but it isn't. Why? Well, depth is different. And that determines a lot of it. The deeper it is, the slower the water moves. The shallower it is, the faster. Right? That's what rapids are. It's because of the huge changes. And also, you know, are you going downhill? Different things. But the idea being at every point in 3 dimensions, the water has a different force at every point. That's what that's telling you. Right? You don't see any constants there. If that was constant, well, that would be more like your faucet. Right? It's all flowing at the exact same rate. All right, I want to set one more problem, and then we want to do some reviewing. I want to leave lots of time for that. All righty. So without even saying it, you're asked for the flux. That's what this is. Cosine x squared minus y cubed, 3y squared z plus 3z squared sine x. And my surface This is really cool. Okay, I can't even imagine you would know what that looks like off the top of your head. I'll just use my graphing calculator. Good luck with that. So I'm gonna give you a hint. It's my personal favorite shape. In Calc 2, when we're learning parametric equations, at the end of Calc 2 and parametric functions, I love doing this one. It's one of my favorites. And this one we often define this way. Let's see, I think, what's the way we usually do it? Trying to remember how we do this exactly. I think we do x equal cosine cubed t, y equals sine cubed t. If I said, given this parameterization, what does the graph look like? I say it's my personal favorite because we study this, we can talk about arc length, we can talk about derivatives and weird stuff. Well, I really want cos squared plus sine squared is 1, don't I? And I can't really do that. But what if I raise both sides to the 2/3 power? Would that be legal? Yes. So then x to the 2/3 plus, equals, and then y to the 2/3 equals sine squared t. So x to the 2/3 plus y to the 2/3 ends up equaling 1. And the graph of that thing, if I take the time and trouble and I do it, again, we do this using parametric equations, and you can literally plot points, we can calculate the arc length, we can calculate the derivatives, but it's basically cusps. I refer to this affectionately as my ninja throwing star. So what do you suppose that one looks like? Points this way. Now it's almost like a little top. Would that be the right term? You've seen the how many seen Inception? You remember at the very end, he spins the thing, and of course it's about to fall down, and it comes back up again, and then you leave the movie going, well, wait a minute, what just happened? Is he still in dream world, or is it? Everybody has the same conclusion. But remember that little thing he spun? Looks like that in every direction. That's what this actually is. That's a cool shape, isn't it? You would never figure this out if you didn't know what this was. That's why I'm showing you that. And I'm asking you to find the flux over this thing. Oy. That sounds absolutely terrifying, doesn't it? Okay, but let's do it. All right, so I want to do the divergence theorem, so I want to do this over Q. So let's figure it out. All right, I'm saying this is going to equal this. So what is the divergence of F here? By the way, to set this one up would be really gnarly because think about your normals. By the way, if you can even picture it, how many surfaces do you have? Remember when I guess? 8. And none of your normals, by the way, are parallel or orthogonal to an axis or to a plane. All your normals in 2 dimensions. Think about the normal. All of your normals are pointing outward, so all 8 normals actually would require some work to figure out what direction they're pointing in. You've got 8 different surfaces, 8 different normals, and you got to, oh boy, and then you got to do it over that. You ready to change the measures now? Well, no, because you have the divergence there. All right, so let's do the divergence. The partial with respect to x is
Negative 6z sine x.
okay. The partial with respect to y is
3 sine, or negative 3y squared.
negative 3y squared. The partial with respect to z is
6z sine x.
with respect to z.
Oh,
3y squared
3y squared.
plus 6z sine x.
Okay. Oh god, this is horrible. Oh. Oh yes. You know, next month when you're still working on the problem because you missed the divergence theorem lecture, you know, the answer's 0. Wow. That's crazy. But that's why you love this. That's why you loved Green's theorem, because you can take really nasty things, and when you're doing the partials, you tend to get something much smaller and more manageable, and every now and then you get lucky and you actually get an integrand of 0. By the way, you don't say the answer is 0 because that's 0. You say, I'm integrating 0, that's why I'm at 0. This isn't the integral, this is the integrand. Don't confuse the two. There's no situation where the integrand equals the integral. You say, but isn't the antiderivative 0? No, the antiderivative of 0 is constant. But then you're evaluating it, and that's why it's 0, because the plus c's and stuff. So that's it. This is divergence theorem. Kind of cool stuff. Okay? This is the last thing of the course. This, of course, is eligible for the final exam. So the flux, the Stokes, the divergence, these are all potential final exam questions. Okay? But they're obviously not going to be on the next test. That stops at Green's theorem, as we know. And that's always one of the gray areas, even though it's really clear on the syllabus when you look at the outline, what's on the test. A lot of folks they lose track. You know, we just had a week off. Yeah, I get the losing track of where we are, so let me remind you. Our last exam was after the first day of integration. So we had just started double integrals. That was the last thing we did. This exam starts with the polar integrals, of which you guys are probably pretty comfortable, and that lecture was October 19th. The exam's on December 5th. That's kind of a long time between. I think that's 6 weeks. We had a week off in there and so on. So there's a lot of material, but it's been a while. This exam has 8 lectures, but because there was also a week off, it really feels like it's extended. So this exam, if we look at the schedule, starts with double integrals, then goes to surface area, then triple integrals, and cylindrical spherical coordinates. So the first 4 lectures was 100% integration. Okay? We'll actually then change the variables, so technically the first 5 lectures. So this exam is going to be mostly integration, okay? But then we get to line integrals, which are low-level integrals. They're just single integrals. The other ones I'm talking about were double and triple integrals. The line integral integrations should be fairly comfortable. You know, independence of path, Green's theorem, okay? Green's theorem is double integral, but at this point, double integrals should be something we're pretty good at, especially if it's of simple regions. So there's nothing on here that you haven't seen multiple times. Now, I'm not going to jinx you by telling you what people do. In Calc 1, I've taught Calc 1 about 1 million times. Obviously, Calc 1 gets harder as the semester goes on. But I don't know exactly how many times I've taught Calc 1 at Mesa. I know it's between 75 and 100. I might be up to 105, I don't know. Only one time was the third exam not head and shoulders above the other 2. Only one semester was the third exam not the best test. And that was a semester where those students were just exceptionally good, so all their exams were great. But in every Calc 1 class I've taught, the third exam is usually 10 to 20% higher than the first 2. Why? Well, also, who's there at the end of the course? You've kind of got things together. It's not abstract. It's just applications of the integral. Boom. In Calc 3, the first exam should be the easiest exam you took in calculus. Why? Because there's almost no calculus. It's just vectors. And the average is usually around, almost every semester the average is around 90%. The third exam, you could certainly argue, is the hardest exam you've ever had in your entire life because it's the end of Calc 3. Yet, of the 3 semesters in every class I've ever taught, it's always the highest average. Of all the calculus tests I've ever given in my life, the third test in this class is always the highest average. I have had multiple classes where the average on this test was over 100% because the extra credit. What? Because you've done everything so many times, there's nothing you haven't done. So it's one of these tests, I'm saying it this way, not to say, oh, it's going to be easy. No, it's going to be hard. It's Calc 3, it's the last test. But when you're going through the problems, you go, I know how to do this, I know how to do this, I know how to do this one. So when you're going, this seems like, I don't feel like very challenged by this question. It's because you know how to do it. How many of you have had that feeling that it seems too easy and must be wrong? Have you guys ever had that feeling? Yeah, I've never had that feeling in my entire life, by the way. Nope. It feels too easy, that means it's easy. That means I know exactly what I'm doing. I have never run into a situation where I questioned the easiness of the problem. If it felt easy, it's because it was easy and I knew how to do it. It was easy to move on. You don't go back and say, I don't know. I got an answer, but I don't trust it. You trusted the process of getting the answer, walk away. If you see an arithmetic error, fix it. But don't question the answer. So this test is different from other tests in that there's no minutia on this test. Go back to the first test. I asked you for the dot product between 2 vectors. Really? And believe it or not, we were only about 75% on that question. I asked you for the cross product between the same two vectors. We were about 40% on that problem as a group, no joke. Now, I mean, you'd laugh. If I gave you 1,000 problems, you're going to be 999 of them correctly. But that problem was small and insignificant, but it was part of the process. There are no minutia questions on this test. They're all big ticket items. Therefore, I have the luxury on this test, like I sometimes do in other classes. In Calc 2, I'm able to do this. All the problems will be worth the same. So therefore, I can give you extra problems. It's one of those choose. Like I give you 14 and you do 12, or I give you 10 and you do 8. One of those kind of situations. I can't do that on all tests. This is the one test I can do it because there are no small problems. If I ask you to find the surface area, that's a bit of work. If I ask you to do something you're using Green's theorem, that's a bit of work. Right? There are no really short, you're out of there in one step problems, like dot product between two vectors. I mean, let's face it, there were problems that were absolutely trivial, weren't they? Right? So there are none of those, but at the same time, there's not going to be 25 questions either. More like 10 questions-ish or something. So part of the reason people do well on this is they're way more focused and they don't worry about the details. Okay? I'm going to give you more questions than you have to do. They're all worth the same. There will be an extra credit. And the idea, and I always remind people, because some people are not good test takers. They just really are. I just gave a test recently in the 116 class. They had a lot of questions because none of them are really long. I gave them something like 23 questions and they had to do 18. It was something like that. And then there was an extra credit. Every single person in the class did all 23 questions. But only a few people got to the extra credit because they ran out of time. I'm throwing up my hands. No, there should not have been a single insurance problem done before the extra credit. Insurance is when you do the extra problems just to be safe. That's great. You don't get extra points for doing those problems. You get extra points for doing the extra credit. So the test taking strategy is when you've done enough problems, now check them, now do the extra credit. If there's still time on the clock, I'll go back and do an insurance. In my Calc 2 class, every semester, the test, I think it might be the first test, and we're doing methods of integration. And I'll give them a certain number of problems. Usually it's like 14 problems, because I can do this in the Calc 2 class. And they're doing methods of integration and maybe some work problems. And I'll say you got to do 10 problems. Every semester, literally every single student gets to all 14. And every semester, literally 3/4 of the class doesn't get to the extra credit. Because they spent another half hour, 40 minutes doing the extra problems that didn't even count. And by the way, I throw up my hands every semester. I have people get perfect. They'll do 14 questions and get them perfect. But they didn't try the extra credit. Don't do that, please. Don't do a single extra problem before you do the extra credit, because you might be able to get the extra credit perfect. But if you don't get to it, there's, you don't get extra points. Insurance is wise. It makes no sense to me to ever turn in an exam early with unattempted questions. Now, let's say I ask you 14 questions and I want you to do 10, I'll just say generically, and you've done 11. Should you try to go do a 12th or a 13th? Nah. They're not going to count. Why? You didn't do them in your first 10. You're saying that's not my best one. And then on the first insurance, you didn't do it on that one either. You understand what I'm getting at? You put it off, you put it off, you put it off. Yeah, you're not going to need to do a 12th or a 13th. But definitely, if I ask you to do 10, definitely do 11. That's what I'm saying. Do that insurance problem after you do the extra credit. Will there be time? Actually, there probably will for every single person, unless you're just bogged down. Now, here's the other thing I warn people about. If every problem's worth the same, you cannot spend any time on one problem. You've got to move on. You have to move on. You look at a problem and go, I know how to do that one, but I know that one takes me longer. Then shove it to the back of the line. Make it the last one you attempt. I look at this one, oh, I can't remember how to do this, and my life depended on it, but maybe an hour later it hits you. I was just talking with a former student, brilliant student, and they were telling me, they said, yeah, I remember taking a test at linear algebra, and with you, and they said, I looked at a problem and went, I have no idea how to do it. They totally blanked. And they said about halfway through the test, while they were working on another problem, hit them, they went back and got it. Of course, they got a perfect score. They used to get perfect scores on everything. And I laughed, I said, nobody does that. Nobody makes breakthroughs during the exam, but this person did. So they did exactly the strategy I said. They looked at a problem, they didn't know it immediately, they moved on, and then it came to them before the end of the test, they went back and did it. Great, that's awesome. So let's look at the practice test. I have the key here. This is very representative, and again, many of you have been with me before. You know that the practice test usually looks a lot like the exam, like exactly. You know, these questions are going to be on the exam. This is exactly what the exam looks like. And you do also notice that none of these questions are really short. None of them are terribly long, but none of them are one step and out. You have to do stuff on every problem. But you have 2 hours. If a problem takes you 10 minutes, that's probably long. But you'd still finish the test easily if every problem took you 10 minutes. Some problems will take you less. The first problem using polar coordinates. If you do that one right, I can't imagine that takes anybody more than about 3 minutes, 2-3 minutes. I mean, there's not much there if you know what you're doing, okay? Now, formulas. Do we have formulas on this test? Yeah, I mean, I'm looking at number one. I don't know that you need to write down, you know, x equals r cos theta, y equals r sine theta, but you certainly can. Is it possible that you could actually blank out on that during the test? Yeah, it's not that at all. It's replacing dA with r d theta. That's the one you're going to forget. Every class somebody forgets that one. You didn't forget it on a single problem all semester, and then on the exam you forgot the r. And it either made an easy integral really hard, or it took something that was a u sub and now it's something completely different. Yeah, the r d theta is the thing you probably want to write down. dA equals r d theta. That's something we derive. That's not an example. That's how you do the conversion. Oh, but then that would also apply to spherical now, wouldn't it? Oh yeah, dv is what? Rho squared sine phi, d rho, d phi, d theta. You think you might want to write that one down? Yeah, because do you know that one off the top of your head? Maybe not. That's the kind of stuff you got to write down. What about the surface area parameter? I doubt anybody needs to write that down. Fx squared plus fy squared plus 1 under the root dA. I would write it down anyway, because again, when you're sitting down taking a test, you want to be able to think instantly. You don't want to be trying to cram everything into your memory banks and then have to draw from it. You will know it, and you write it down so that if you do blank, you just glance at the card. But by writing it down, most of you know you're never actually going to look at the card. But it's there. It's safety. It's your parachute. Those are two that I absolutely recommend that you write down, because spherical may be the most obscure thing of all. Okay, now moving down the road, the center of mass. This is the moments, not the center of mass, it's the moments that people tend to forget because they don't look like the Calc 2 moments. Right? The moment is not to an axis, it's to a plane. So the moment to the xy plane involves z. Right? So we don't forget that, oh, okay, so it's the exact same formula as the mass. Right? I'm integrating the density over the volume, but now I have this. What if it's only a two-dimensional problem? It's the same thing. I multiply the x when it's the moment to the y-axis. I multiply the y when it's the moment to the x-axis. Not Calc 2. Calc 2, we had one independent variable. Here you have two, because your density is going to be a function of more than one variable. Density problems are not hard, but sometimes we forget the detail. I don't know that you need to write 2 and 3-dimensional, but write one of them down probably. Let's see. Well, there's no formula for volume. You just have to know your boundaries. And how do you decide whether to go polar versus cylindrical versus spherical versus rectangular? Is it the integrand or the region, do you think, more often than not, is going to determine? Probably the region. You can integrate, you know, if I have x squared plus y squared as my integrand, but my region is rectangular, I'm going to stay rectangularist. But if I have x squared plus y squared under a square root, that's where I get in trouble. Okay, that I'm going to have to go polar. Right, because I can't do that one rectangular. But as you've noticed, they usually kind of go hand in hand, don't they? If it's a polar region, then it's usually also a polar integrand. If it's a rectangular region, it's probably a rectangular integrand. I think today's question on Green's theorem, this is a perfect example. On the first question, and I love asking this question, on the first question, your region is a semicircle. It's like an, oh, duh, of course I'm going to go polar. How many kept it rectangular, by the way? Usually it's about half and half, because you realize, oh, actually that's not that bad. Yeah, I got a square root, but I ended up squaring it. It ended up not being icky at all. So I gave you one on purpose that it's basically the same work whether you went polar or rectangular. Most people would automatically go polar because of the circular boundary. But if you left it rectangular, you found the integration wasn't that difficult. And you were probably questioning yourself going, wait a minute, I should have gone polar, but I didn't, and it still worked. Yeah, you can get lucky. I have something rectangular or not, but my integrand has x squared plus y squared, maybe 2 integer powers. I don't have to go polar with that integrand. Square root, yes, I'd have to. So you always have the choice, and you just say, okay, what's going to be easier? Keep moving on. Volumes, Jacobian. I will not make the region complicated. I'll make the region really simple like this. This was a very simple region. You got to draw the region because you got to figure out what the boundaries are in terms of lines. Otherwise, you won't be able to figure out the limits of integration. A lot of people try to do this without a picture. And then they wing, and they got lucky and got the limits because they did some really weird substitution. I'm like, what did you do that for? I mean, you're having 2 lines intersect on the XY plane. You need to know that point of intersection because that's how you're going to determine your limits. But the one thing that people forget in the Jacobian, what do you think it is? The absolute value of the Jacobian. The Jacobian is the determinant. This is why the notation can be confusing. The Jacobian is the determinant. The Jacobian is not a matrix. It's the determinant of a coefficient matrix. So the Jacobian is a determinant, but as we know, the Jacobian is going to be negative how often?
50%.
Exactly 50% of the time because your substitutions are random. Oh, so since the Jacobian can be negative, my Jacobian ends up being, negative, negative UV. Okay, then I want the absolute value of that in my integral, or my final answer will be the opposite sign. Because the substitution was arbitrary. Okay? A determinant isn't an absolute value. Your determinant can be negative, and then when you put it in the integral, you take the absolute value of that. And a perfect example, on this particular quiz, I don't know if I told you what substitution to use. So I got a lot of people that got negative Jacobians, and then they took the absolute value correctly. But if I don't take the absolute value, again, I'm going to get the opposite sign of my answer. That's all. So the Jacobian, but don't forget it shows up here. And the Jacobian, remember, it's the determinant of the partial derivatives. I will only ask you a 2-dimensional problem. I'm not going to ask you 3-dimensional. You could do it, but it would take a really long time. There's no efficient way. That's just scary. And in reality, it'd be very rare that you run into that problem. I mean, you might run into that problem in an upper level physics situation, but it's really obscure. 2-dimensional, that's not too bad. Now, the definition of divergence and curl, certainly you could write them down because I don't want you to flip them. Divergence, think of it as that dot product, scalar value function. Of course, curl we know. Think of it as cross product because that's technically what you're doing because you're getting a vector valued function in the end. You can't afford to get those incorrect. Now, is there a check for divergence? No, I just have to be, just be careful. There's no check. Is there a check for curl? No. When you did cross product at the beginning of the course, there was a check. You just dotted it with one of the original vectors. That was the easiest check on planet Earth. But when you're doing the curl, there's no check in terms of, can I dot it with something else? It won't work that way. Because you didn't find it by finding a cross product of vectors. You made a vector of partial derivatives. It's not going to be orthogonal to another vector that you know of. Unfortunately, you just got to be careful. That's it. Darn. Now, when you're doing the test for independence of path, in 2 dimensions, it's easy. Is nx equal to my? It's actually a piece of cake. But in 3D, you're not testing it that way. That one, the curl vector has to be the 0 vector. If the curl vector is the 0 vector, then your force was conservative, therefore your integral is path independent. Then that means there is a potential function. If your curl vector is not the 0 vector, it's not conservative, the integral is not path independent, but more importantly, there is no potential function. There's a danger that I will give you, by the way, this happens every class. I will give you the situation, I'll give you the force vector, and I'll say, find the potential function if it exists, and people will start their integration right there and then. But it wasn't conservative. So they're spending a lot of time and energy finding something that doesn't exist. Or worse, they actually find something. It can't be correct, because if it's not conservative, there is no potential function. So you always got to check for conservative first. Okay? The question number 10 looks a lot like the one that was just on the quiz, doesn't it? Okay? This is the work done where I gave you the force and I gave you the parameterized curve, and you did F dotted with the RDT. That's a very standard problem. There's no way I'm going to ask that question and it be hard. That question just can't be difficult. But I had a lot of questions before that last quiz. People said, I'm not sure how to come up with my R or my limits. And I said, well, your R is right there. I told you X, Y, and Z. R is exactly, X of t, Y of t, Z of t. You don't actually do anything. I'm giving you the R without calling it R. Now, how do I know my limits of integration? Well, if X is t, now go over, I went from 0, 0, 0 to 2, 4, 8. X is obviously going from 0 to 2. Now, Y is t squared. Oh, I'm going from 0 to 2 squared. Okay, then, right, the numbers have to work. If the numbers, this one went 0, 0, 0 to 2, 4, 8. If I went 0, 0, 0 to 2, 4, 7, it's an impossible question with no answer, because it means I totally messed it up. That's not going to happen. You're not going to have an impossible question. Okay? Number 11, I'm asking you to evaluate that thing, which means that if I ask that question, I'll say, show it's conservative first, the vector, or show the integral's path independent. And then what you have to do is go through and find the potential function. It's not complicated, but there is a series. Now, there is an error that crops up that I see every single class, and a lot of people think they're being clever and saving some time. When they get near the end, and you're to the last one, you had your g of x comma y. And by the way, I've seen a lot of g prime of x comma y's. I've been doing math a long time. I actually don't have any idea what that means. You can't have a prime with two independent variables. You're not even suggesting which variable you're taking the derivative. There's no g prime of x, y. There's the partial of g with respect to x, or there's the partial of g with respect to y. There's not a prime in there. I can have an h prime of z because there's only one variable. So I've got this g of x, y, I got the partial, I'm comparing them, and now I'm integrating, and now I'm doing my last partial derivative to get the z. People are only taking the partial of g, they're not taking the partial of the original f. I find that in the last quiz, I had a lot of people just taking the partial of z. And it worked and you got the right answer because I didn't have any functions of x, z. In the original function, if I had had a function of x, z, then every part of the answer would have been 100% incorrect. You can't take the partial of the g to find the last function. You have to take the partial of the entire f that you've created. Does everybody know what I'm talking about at that point? In this problem here, you just found g of x, I'm looking at number 11. G of x, y, you found to be, hold on, y squared z cubed. So now you restate the original f, if I can find it on here. Hold on. This is too crowded for me. Oh, now the original is 2x squared y plus y squared z cubed plus h of z. And now I take the partial of this with respect to, sorry, x, y, z. Now I take the partial of this with respect to z and compare it to the p. But what most people are doing is they're going, no, I'll just take the partial of this and then it works. Does it always work? No, actually it'll probably work less than 10% of the time. You just got lucky on the quiz because I had no functions that were x times z. If I have a function that has an x times z and you're only using this, then you're not using the function of x times z, which means you will not get the next h of z term correct, and the whole answer is wrong at that point. So don't take the partial of this to finish the problem. The h does not come from this, it comes from this. They got it? And people think they're taking a shortcut because it worked, because I gave you really simple f of x, y, z's. If your f of x, y, z is a little bit more busy, it won't work. So you got to go through the whole process. It's not short and sweet. Now, the Green's theorem problem, I will not say use Green's theorem. I don't have to. I'm going to give you an integral, a little circle on it. That means you know you have a closed loop. Is it possible to do without using Green's theorem? Yeah, but it means you have to do multiple line integrals with multiple parameterizations. There's no advantage to that. In fact, I don't think I could come up with a problem that it would be faster or easier that way. So no, you see the circle in the integral? Green's theorem. Don't even give it a second thought. Okay? Automatic. Now, there are 12 questions on this practice test. This is over 8 lectures. This is pretty much one question from each topic. This is what the exam is going to look like. One question from each topic. All worth the same, like I said before. No one problem is more important than any other problem, and of course there'll be an extra credit. Now, here's the great advantage a lot of you have. Many of you have had 2 solid exams, so you've already figured out, I don't have to ask you. I know you figured it out down to the point. How many points do I need to avoid the final exam? And that should be your ultimate goal. I don't want to take the final exam. If you have 2 solid exams, you can do that. But remember, there's still a handful of quizzes left. And here's what happens in every calculus class I teach every single semester. It's the exact same thing. After the last exam, there's still a few quizzes left. Your accumulation, your total points put you at a particular place, but maybe you're a little bit short of the next threshold. Maybe you're 30, 40, 50 points short of the next threshold with the few quizzes remaining. Every class I teach, it's interesting. It's the numbers I look every semester in every class. It's always between 5 and 9. I don't know which 5 to 9 people, but there's usually 5 to 9 people who, after the last exam, are quizzes away from the next threshold. I can't tell you because I don't know what your score is going to be, but your score was good enough, or maybe it was lousy enough, to put you short, but you can still reach there with the quizzes. Now, having said that, every semester, there's a few of those 5 to 9 that don't bother doing the last quizzes. So they basically give up the potential grade, or they say, oh, I'm just going to go ahead and take the final. Why? I mean, you got a physics final probably the same day, and maybe the OChem final, and why in the world would you put yourself in that situation? But every semester, there's people that just won't do the last quiz or 2. I've had it where in some classes I've had 3 to 4 quizzes left. You're less than 10 points. You don't bother doing the quizzes. Heck, if you write your name correctly and only have one of your names misspelled, I'll probably give you 5 points. Right? But every semester, and I'm pleading with you, please turn in the last quizzes. Please, even if you're not taking the final, turn in the last quizzes. Ensure that you've reached it. Now, you'll all know because the grades will be posted. The test is on Monday. You're all coming on Wednesday, I hope, next week. Now, I'm going to mention this because I don't know. Let's go ahead. I'm going to turn this off because I'm done with this part.